In today's mini lecture, we are going to talk about the rotational equivalent of Newton's second law. We're also going to talk about angular momentum and rotational kinetic energy to wrap everything up. Now, what I haven't really talked about is that actually angular velocity and angular acceleration are vectors, just like how linear velocity and linear acceleration are vectors. We're not really going to use that vector idea too much for the angular velocities and accelerations, but I still do want to talk about them. So for your angular velocity, the angular velocity represented by the Greek letter omega always points along the counterclockwise axis of rotation, points along the axis of rotation. And in order to figure out the direction of omega, you use your right hand. Okay, so you figure out which direction is your object rotating. Okay, you take your fingers curl around in the direction of rotation, and your thumb points in the direction of the angular velocity. Okay, so in this image that we have here, our direction of rotation is following that red arrow there. And then, so if I take my fingers and curl them around the direction of the rotation of that disk, my thumb points in the direction of the angular velocity, which is up in this case, okay? And alpha also points along the counterclockwise axis of rotation too. So if you figure out your direction for omega, then you can figure out your direction for alpha, which is your angular acceleration. So just with linear acceleration and forces, we had that the force was equal to mass times acceleration, Newton's second law. Now for rotational motion, our rotational equivalent is that the torque equals what we call the moment of inertia times the angular acceleration. So instead of force, we've got a torque. Instead of mass, we have what we call the moment of inertia. And instead of linear acceleration, we have angular acceleration. Okay, so for example, here we have a bicycle that's rotating around the front part of the bicycle here. Okay, this is our axis of rotation. Our bicycle is rotating with some angular acceleration, and there's a force that's being applied here by the hand. That force applied by the hand is giving that object some angular acceleration, and we can calculate that angular acceleration by figuring out what the torque is from this force and setting it equal to the moment of inertia of this tire times the angular acceleration. So the moment of inertia is a quantity of any object that's executing rotational motion. That's sort of the rotational equivalent for mass. An object's moment of inertia depends not only on the object's mass, but also on how this mass is distributed about the axis center, about the rotation axis center. So the moment of inertia of a collection of a bunch of particles is just going to be the sum of that particle's mass times their distance from the rotational axis squared. So whatever that object is, it has a bunch of mass particles. You figure out all those mass particles, you get the mass of those individual particles, you figure out their distance from the rotational center, you square that distance, and that's the moment of inertia, sum of all of that. So the moment of inertia of any system is equal to the sum of all the individual mass pieces times their distance away from the rotation center squared. Okay, so for example, here we have a rotating disk that has a moment of inertia of its own. And then we have 4 people on the edge of that rotating disk. So the moment of inertia of the system is going to be whatever the moment of inertia is of the disk itself, plus the moment of inertia from each of these individual persons sitting on the edge. That moment of inertia is going to change when those people move toward the center of the rotation axis because the distribution of masses changes in that case. So when these people are further out, this object has a greater moment of inertia. So for the moment of inertia of this system, we've got the moment of inertia of the disk itself, plus the moment of inertia of each of these individual people, which is going to be their mass times their distance away from the center squared. So you've got moment of inertia of the disk plus m of this person, mass of this person, times r squared plus mass of this person times r squared plus mass of this person times r squared, and so on. So whenever those people move closer to the center, you're going to reduce the total moment of inertia of the system, because now the moment of inertia of the disk itself is the same, but these people, they have a different distance away from the center of rotation. That distance from the center of rotation is smaller, so their individual contributions to the total moment of inertia of the system is going to be smaller. So this system here would have a smaller moment of inertia. Larger moment of inertia, it's going to be harder to get the thing to rotate or harder to slow it down. Just like inertia with linear motion. The larger the mass, the harder it's going to get that object to speed up, the harder it's going to get that object to slow down. Now the units of moment of inertia are mass times distance squared, so kilogram times meter squared. Here's what you're going to do for this first engagement check question. You're going to interpret the moment of inertia of a system. So we're going to consider these 4 systems down here and the distribution of objects on a massless disk. To which system will you need to apply the largest torque to maintain the same angular acceleration if the system of masses is rotating? So, okay, well, which system will you need to apply the largest torque if their angular acceleration is the same? So remember, torque is equal to moment of inertia times angular acceleration. So to figure out which system do you need to apply the largest torque to keep the same angular acceleration, you're going to have to figure out which system essentially has the largest moment of inertia. If angular acceleration is the same for all of these objects, the object that you're going to have to apply the largest torque to maintain that same angular acceleration is the object that has the largest moment of inertia. So essentially I'm asking you, to which system will you need to apply the largest torque to keep the same angular acceleration? That's also the system to which you're going to have the largest moment of inertia. Okay, so you get to evaluate the moment of inertia of these systems. So this disk on top of which these 4 masses are rotating, that disk doesn't go into this calculation. Okay, for A, we have this massless disk, and so the disk moment of inertia doesn't go into it. But you have these 4 masses. And the moment of inertia, remember, is the sum of the individual masses times their distance away from the rotational center squared. So for each of these systems, you're going to have to find what is the mass and how far are they away from the center rotation axis squared. Okay, so to find the moment of inertia of this first system, you're going to have to take this mass times its distance from the center squared of rotation squared, plus this mass times its distance from the center of rotation squared, plus this one, okay? Plus this one's mass times r squared, plus this one's mass times r squared. So you're gonna have 4 masses times r squared for this one. And then you're gonna do that calculation for each of these. The r will change and the mass will change. So essentially you're gonna find which one of these systems has the largest moment of inertia. That's the one you're going to have to apply the largest amount of torque to in order to maintain the same angular acceleration. We can piece together the angular acceleration of a system by looking at the sum of the mass times r squared of all the particles. But we can also look at a chart in order to give us the moment of inertia for a bunch of different shapes. This is also a table that's in your textbook, so you can look at that table in your textbook. So for example, here at the top, we have a hoop that's rotating around a central axis, okay? The central axis is in here and the hoop is rotating around it. So the moment of inertia of this object is gonna be its total mass times its radius squared, okay? And then let's say, let's go with this one down here. We're gonna see this one in another problem. We have a long, thin rod with a length of L, okay? And it's going to rotate about an axis through one end perpendicular to its length. So it's going to rotate about this axis. This is its rotational point. And so it's going to make a big sweep around this central axis right here, okay? And as it does that, its moment of inertia is going to be its mass times this length squared divided by 3. So 1/3 ml squared. So here we have a solid sphere rotating around any diameter. Its moment of inertia is 2/5 its mass times radius squared. So whatever the object is in question in the system, you can always come here to this chart and look up what should the moment of inertia be. You might have to add some moments of inertias together for different unusual systems. And if you're thinking about something as a point mass, its moment of inertia is always its mass times r squared. So where r is the distance that mass is sitting away from the rotational center. So we're going to use that idea with torque is equal to I alpha and incorporating moments of inertia and also using our rotational kinematics equation in order to solve a problem related to baseball.
In this problem, we're going to apply our rotational equivalent of Newton's second law to a real-world problem, to baseball. So we have a baseball player, and they are going to toss a 1.5 kilogram baseball, and we have our arm that is going to do the tossing of that baseball, okay? And so we have a forearm right here with a mass of 1.5 kilograms, and it has a length of 0.35 meters. Okay, so this is going to be the arm around which we're pivoting with our elbow in order to have that baseball in our hand and toss it like this, okay? So we have to find a couple of different things with this problem. We're going to start our ball back here at rest, and we're going to toss it with our arm, and we're going to release it with a speed of 30 meters per second over a time period of 0.3 seconds. So I wrote all of that down right here. Those were our knowns. We've got the baseball of 0.15 kilogram, our forearm, which is this right here, is going to have a mass of 1.5 kilograms. Everything's going to pivot around our elbow right here. The distance between, which is the length of our arm, the distance between the elbow and where our baseball is, which is the length of our arm, is 0.35 meters. We're going to launch this ball. We're going to start it here from rest to a speed of 30 meters per second over a course of 0.3 seconds, and then we're going to let it go. Okay, so our first step is to find the constant angular acceleration of the arm and the ball, alpha equals question mark. So the constant angular acceleration while we're still holding onto the ball. So this whole thing of our arm plus our ball. What is the constant angular acceleration of that system? Well, in order to find that, we are going to use our equations for kinematics. So we need to find our angular acceleration alpha. And we know a couple of pieces of information. We know these linear speeds here, and we know a time. So let's just look at our equations for rotational kinematics equation sheet, okay? And there's one equation here, omega final, that's our angular speed, equals omega initial plus alpha t. Alpha is our angular acceleration, okay? So if we're starting from rest, we have no angular speed. Now we can get our linear speed into this equation right here because we know that our angular speed, that's omega, equals our linear speed divided by r. So where I see omega final here, I can replace that with v final over r, and that equals alpha times time. So my equation for alpha is going to equal v final divided by r times time. Okay, so r, remember, is our distance between our elbow and where that baseball is. It's also the length of our arm, okay? So the baseball is going to be executing circular motion at the distance r away from the pivot. And our final velocity was 30 meters per second, and we're going to divide it by the length of our arm, 0.35 meters, times the time over which we're accelerating this ball through an angle, and that's 0.3 seconds. So our angular acceleration of the system is going to be 286 radians per second squared. Our angular acceleration will always have units of radians over seconds squared, okay? If we put velocity here in meters over second, distance in meters, and time here, okay? Because technically here we've got the meter cancels with the meter, and we're left with units of radians over seconds squared, okay? So that's part A. Part B is to find the moment of inertia of the system consisting of the forearm and the ball, okay? So our moment of inertia, I, total, of our system is going to be the moment of inertia of our arm plus the moment of inertia of the baseball. Okay, so we can look at the table in our textbook for moment of inertias of different systems. We can approximate our arm right here as a rod rotating about an axis through one end perpendicular to its length. We can assume our arm is like a rod. It's going to be rotating through an axis right here perpendicular to its length. And the moment of inertia of that object, a rod rotating around an axis perpendicular to its length, has a moment of inertia of 1/3 times the mass of that object times the length of that object, which is what I'm calling R here. That's the length of our forearm, squared. Okay, 1/3 mass times R squared is the moment of inertia of a rod rotating around an angle perpendicular to one end. Okay, and then the moment of inertia of our baseball, we can assume that this baseball, we can approximate it as being a point mass at some distance from a rotational center. And the moment of inertia of that would be the mass of the ball times R squared, which again is our distance away from our rotational center, which is here, our elbow. So this is R, okay? And so we plug everything in to get our moment of inertia. That's 1/3 times the mass of our arm, 1.5 kilograms, times the length of our arm, 0.35 meters squared, plus the mass of our baseball, 0.15 kilograms, times the length of our arm, which the ball is sitting at the length of that, 0.35 meters squared, okay? And so then we find that our total moment of inertia for the system is 7.96 times 10 to the minus 2 units of kilogram times meter squared. So those are our units of inertia, kilogram times meter squared. Okay, and then for part C, we need to calculate the torque exerted on the system that results in this angular acceleration coming from A. So we have to find the torque in our system. The torque in our system is equal to the moment of inertia of our system times the angular acceleration of the system. Okay, so that is why we calculated the angular acceleration in part A, why we had to find the moment of inertia in part B, so we can eventually find the torque, which is going to be just the multiplication of these two pieces. So we take our moment of inertia here times our angular acceleration, and that will give us our torque in units of Newton times meter, and that's going to be 22.8 Newton times meter. So let's look at our units. We've got the moment of inertia, which is kilogram times meter squared, and then we're multiplying it by our angular acceleration, which is radian over second squared. Okay, the radians kind of magically disappear in a puff of smoke. So this is kilogram meter squared over second squared. So a Newton is a kilogram meter over second squared. So this is equal to kilogram meter over second squared times meter. So that's our Newton times meter. Okay, that's how our units work out for this problem.